Hello, sir.
Yes, hello.
Sir, actually, on behalf of that entire MM681 students, sir, actually, we wish
Uh,
you that happy Teachers' Days.
oh, thank you
Actually,
so much. Yes,
September 5th is we don't have any class, sir.
yes,
So,
yes.
actually, we will tell in advance. So, happy Teachers' Day, sir.
Thank you
Actually,
very
we'll,
much. Yes,
yes, sir,
thanks so
actually,
much.
can I speak a minute, sir, here, if possible?
Yeah, yeah. Take your time. Yeah. So,
Actually, sir. Yes, sir. Actually, it's a very, actually, I feel very blessed to have a lecturer like you, sir. Actually, you are, the way you are teaching as well as that way you are giving the commitments to taking class is excellent, sir. Actually, so, actually, it's a proud moment for us. So, we get a professor like you. So, thank you so much for your service, sir. Actually, we pray God to give good health for you and your family. So you will give this service to the year on year. So the upcoming student community will also get benefits, sir. So once again, thank you for your service and wish you happy Teachers' Days.
thank you so much, Saktivel. I think, yeah, I'm very, yeah, proud of this movement. Okay. So I'm happy to, yeah, hear from you, from all of you. You said on behalf of whole car, of course. Okay. So anybody can also speak. Okay. We have enough time now. If somebody wants to say any words, yeah.
So thank you for all your contribution, the way you conduct the lectures, the way you maintain discipline, and the way you take doubts, and the way you take doubts after the class also. All that actually encourages us to take up this course and encourage other students to take up this course. So thank you for that, sir, and thank you, Saktivel, for putting this up. Thank you.
Thanks, Monish. Yeah, thanks. Thank you so much. Yeah. So anyone else wants to speak?
Thank you, sir. This is Sudha, and happy Teachers' Day. Uh, Actually, this subject was very difficult for me, and this location all kind of was I never understand, and now I'm getting what exactly those are, and it is very important to be a methodologist to it is very important to know these basic things. So, sir, I'm getting those things, and I'm getting very well. So, the uh, you taught you are teaching in a very different manner, and I think it is easy for everyone. I think so. You are making, and
Thanks,
thank you, sir.
Sudha.
Thank you,
Thank
sir.
you very much. Yeah, for your wonderful words. Okay, yeah. Anyone?
Hello. Yes, sir. Good
Yeah.
morning, sir.
Yes, Kushagra,
Yeah,
please.
yeah. Happy Teachers' Day, sir, in advance.
Thank you.
So,
Thank you.
yeah. So on the same line as my batchmates, like the way you are teaching, specifically the time you are giving for the doubts, because I feel in these subjects the concepts are more important, like the theoretical. Being very honest with you, initially I thought this will be a like a theoretical, a boring sort of lecture. But now at this point, I am pretty sure that this is a subject which I'm enjoying the most. Like I don't want to skip the lectures of this subject. So all credit goes to you. Even I've taken other subjects which have numericals, but once I attend these lectures, so if the concepts are being clear, so we gradually like develop our interest. So that is happening at least with me. So I'm definitely enjoying the subject. In this semester, this is my favorite subject.
Thank you.
Yeah, thank
Thank
you.
you so
Thank
much,
you.
Kushagra. Yeah.
Hello, sir.
Good morning, sir.
Good morning, Kania. Yeah.
Yes, sir, and happy Teachers' Day, sir.
Yeah. Happy Teachers Day. Yeah, thank you.
Sir, I am from mechanical background, but I thought that this subject will have more part of mechanical like stuffs, but the things which are in this course are mostly in the from the background of metallurgical type. But the way you taught the subject, I feel very easy to grasp uh, all the matter that is inside this course. But I feel it's good for me, and I'm fortunate enough to choose this course. And thank you once again for this.
Thank you, Kaniya Kumar. Thank you.
Hello, sir.
Yes, Ravi Shankar. Yes.
First of all, happy Teachers' Day in advance to you, sir.
Thank
And
you.
thank you for letting us to go through this course. We have seen your presentations, and if we have noticed that for every slides the references are changing, so we can understand that how difficult it is to maintain that customized course for us, and then teach us in such a way that the link up should not get break in between, and every background of a student, whether it's chemical or mechanical or metallurgy background, will be able to understand that. And the second thing is that the practical applications that you have tried to explain to us, that will be definitely helpful for us for our future projects that we are going to take. And we are very thankful to you for giving us these many of lectures and the opportunity to learn. So thank you very much, sir.
Thank you, Ravi Shankar. Thank you very much. So, anyone else wants to say? Yeah. So, thanks a lot for all your comments and compliments. So I feel very much happy the day. I think this is the first time I think students have directly told in the class about my lecture, kind of style what I'm following. The feedback is a direct feedback. I appreciate. Thank you so much for all your inputs. And your compliments on my teaching performance. Thank you. So I think let me start. I think today's lecture. So happy Teachers Day to all of my colleagues and others. Thank you so much. So, are you able to see my lecture slide?
Yes, sir. It is visible, sir.
Okay, thank you. Okay, so I think let me give some recap about last previous lecture what we discussed. So we had basically major discussion is complete discussion is basically related to Hall page relationship. So I could, I think, spend around 1.5 hours on Hall page relationship. There's a lot more story to talk about Hall page relationship, but what I given some of the important aspects related to Hall page relationship. It is a very interesting equation which was developed based on experimental findings. Okay, so where actually Hall and Page, two scientists, within a 2 year span of time, whatever observations they have made on iron when it was deformed as a function of different grain sizes at different grain sizes when it was deformed for different grain sizes, so they established how yield stress is going to vary with a grain size. So the kind of equation what they arrived from the experimental findings is basically stress is proportional to inverse of square root of d. That was the relationship governing. This is a kind of governing equation which was proposed by both Hall and Page simultaneously. And basically within a 2 year span, so both of them have come up with this kind of relationship. So that's what people call it a Hall Page relationship. It's basically a governing equation which describes how yield stress of a material is going to be depend on grain size of a material. So here this sigma y is equal to sigma naught plus k t to the power of minus 1 by 2. So sigma naught and k are called Hall pitch constants simply. Each one of them has its own physical meaning. The sigma naught basically considers the friction stress which is required to move individual dislocations from micro yielding slip band. In the talk about micro yielding. So in the kind of friction stress which is coming as a function of several components depending on alloy, depending on deformation, amount of deformation, how much it's taking, and what is the polycrystallinity in terms of a crystallographic nature, texture nature. All those things will be part of this friction stress. Piles Nabarro stress, solid strengthening, particle strengthening, dislocation based strengthening, and substructure formation within a grain. We may see some subgrains; those can also contribute. And we are talking about texture based. Texture. If there is a metal is texture, so we do have some texture effect. So all those things will be part of sigma naught, and k is basically called dislocation locking parameter. It is simply indicates that what is the difficulty of spreading yielding from one grain to other grain in polycrystalline materials. That means what is resistance that is being offered by the boundary for the dislocation motion. Okay, that basically considers dislocation locking parameter. Then, okay, so we discussed, okay, the sigma naught and k values are going to depend on various, okay, going to get changed depending on what factors, okay, we are considering. So if we talk about crystal structure, stacking fault energy, testing temperature, and heat treatment, okay, these kind of four important things I considered, how this is going to dictate the sigma naught and k values. Okay, so this I think we had enough discussion about these variables which can influence Hall pitch constants. Then we had actually, okay, I had showed, okay, typically we do see linear deviation if you make a, okay, plot with respect to stress or hardness as a function of d to the power of minus 1 by 2. D is a grain size. Okay, it should supposed to give you a linear line. However, recent, okay, in the last, I think, 3 decades, there's a huge amount of, okay, work, experimental work has gone into to produce fine grain size materials. When people started producing fine grain size materials less than 1 micrometer, people have reported deviations from the regular Hall pitch behavior. So the deviations can be a change in slope. That means K can be changing. Okay, and this deviation can also undergo inverse kind of thing. Okay, inverse Hall pitch basically means, okay, stress is directly proportional to, okay, here what you are talking about, stress is actually directly, okay, inversely proportional to grain size. Finer the grain size, higher the stress according to regular Hall pitch behavior. In case of inverse Hall pitch behavior, your sigma y is a function directly proportional to d to the power of some slope. To the power of some slope. That means actually grain boundary weakening mechanism going to contribute, okay, this kind of, okay, inverse Hall pitch behavior in a fine grained materials. So this has been, okay, well established various in various materials. This is a summary one, okay, plot which basically summarizes some of the data findings on nickel based, okay, materials where people have reported, okay, presence of inverse Hall pitch behavior. Okay, so then, okay, I discussed, okay, only about the what are the mechanisms people have explained so far, okay, to describe, okay, this relationship, to derive this equation, okay, how sigma is going to depend on grain size of a material. So that there are two categories of theories. One theory basically tells about, okay, one theory basically tells about based on the dislocation pile-up based mechanism. The other mechanisms basically based on non-pile-up theory mechanisms. Okay, so in under, okay, pile-up theory, we do talk about Hall and Pitch and Cottrell have given, okay, kind of they consider dislocation going to get piled up at the boundary. Okay, so the dislocation can burst through, okay, after certain amount of, okay, pile up, or can also initiate yielding in adjacent grain. Okay, the Frank Reed source can be can be initiated in adjacent grain because of stress developed. So according, basically the Hall and Pitch will basically discussed dislocation can burst through the boundary according to Hall and Pitch. Whereas Cottrell, what he said, the stress constant whatever is building up, that can actually generate, okay, that can initiate Frank Reed source in adjacent grain, then yielding can take place in adjacent grain also. So that's how it's like a kind of thing, okay, people have discussed in terms of a pile-up theory. The problem with the pile-up theory, okay, so the observations are in steel. Okay, all the observations, initial observations are actually on steel. But when they did microscopy, ultra microscopy, people did not find out, okay, piling up of a dislocations in the material like a iron and also in aluminum, high stacking fault materials also. We do not see piling up a dislocation because this is actually aluminum is a high stacking fault material, and BCC alpha, BCC iron also relatively high stacking fault energy material. So people did not observe pile-ups. That's why people are ruled out. Okay, said we cannot consider pile-up theory is going to be applicable to arrive the equation which describes how the stress is going to depend on grain size of a material. So later people come up with Lee and, okay, some other work hardening theories and composite models to explain how, okay, dislocations, okay, are going to play a role, okay, in terms of a grain size effect. So the grain size, okay, if it consider grain size, according to Lee theory, boundaries in a polycrystalline material boundaries will contain some ledges. Okay, very tiny ledges will be present in the boundaries. Those will be source for the dislocations. Dislocations are going to get generated, okay, from the boundaries, and those dislocations going to traverse into the grain, okay, and they can form some forest dislocations within the grain. Some dislocations will be left out as a forest dislocations for further dislocation. Okay, resistance going to be offered by these forest dislocations. So the density of forest dislocations, okay, is considered to derive at, okay, how the stress is going to depend on grain size of a material. So number of ledges and dislocation density are going to related, and one can, okay, arrive at this equation by, okay, using a least theory. According to work hardening theory, which basically indicates the trapping of gliding dislocations. Dislocations are going to get trapped within a grain. Okay, when you deform a material, okay, one can actually trap the dislocations within a grain. So that can give you, okay, the relation sigma, okay, proportional to, okay, d to the power of minus 1 by 2. So this theory is used to explain flow stress at any given stride. Okay, can also, it basically it says that it also depends on grain size of a material. Okay, this is about actually two now. Okay, actually one, okay, there are actually three pile-up theories: Hall theory, Page theory together, Hall Page theories, and Cottrell theory, a common category of pile-up theory, and ledges, okay, theory basically it's called Lee's theory, and work hardening theory, and composite model. Okay, these three come under category of non-pile-up, okay, theories based on non-pile-up. Okay, dislocation will not pile up, but actually, okay, grain boundaries, okay, are going to affect the deformation behavior of a material. Like the stress is going to depend on, okay, inverse d to the power of minus 1 by, is inverse proportional to, okay, square root of d. So this kind of, okay, equations have been derived, okay, mathematically by using some assumptions. By using some assumptions, people have arrived at how the, okay, Hall-Page relationship can be derived. Okay, I guess I think at this point I stopped my previous lecture. Are there any doubts? Because that was the end to the Hall-Page, okay, relationship. So if there are any doubts, please
Sir?
let me know. Yes.
So in the work hardening theory, you said that dislocations can get trapped, right? So materials with low SFE, they will trap more and more dislocations, and hence you can see that effect about the relationship you just showed. Yeah, that one,
Yes.
right? So
Yeah.
that dislocation trapping effect will be more in lesser stacking fault energy materials. Okay.
Yes. That's what. Okay. So because see, some of these things could not, okay, not necessary to be in low stacking fault materials, even high stacking materials, some dislocation can be trapped. Okay. So the only thing, accordingly your K is going to change. Okay, what they say, the K value is going to change depending on stacking fault energy. Okay, that's what we already shown one experimental observations. Okay, so according to this theory, okay, the amount how much dislocations are getting trapped, okay, that basically density, okay, within the grain are going to vary depending on stacking fault energy. Okay, so that basically dictate your KHP. Okay, the Hall-Page constant K.
Yes, clear.
Yeah. Any more doubts here? I think because we have to move on to a next topic. Is it clear? I think about Hall-Page relationship. Okay. So if there are no more doubts, I think let's move on to next topic. Okay, yield point. Okay, phenomenon. Okay. So I think this is one of the important, okay, aspects as far as industry is concerned, steel industry is concerned. The steel industry works on, okay, low, okay, when you talk about not only steel, means automotive industry also. So automotive industry uses a lot of steel. Okay, most of the steel actually will be having a low carbon steels, low carbon steels. So the steels containing very low amount of carbon, okay, will undergo, okay, this kind of, okay, stress strain behavior. The stress strain behavior, okay, can be of this kind of nature. Okay, so this is a very interesting observation. Okay, it was reported in 1840. Okay, around 1840, 42. Okay, around that time. Okay, the first observation about the, okay, this kind of stress strain is not a smooth, okay, flow curve. So initially there is a elastic deformation. Okay, after some amount of stress, there is a drop in yield stress. Okay, this is called sharp yield drop has been observed in certain class of materials like steels containing very low carbon or low nitrogen content. And after drop, okay, there is a some almost like a constant, okay, okay, almost constant stress with slight serrations, with slight serrations, okay, in the, okay, stress strain behavior. After certain amount of strain, it follows regular trajectory, okay, regular trajectory of work hardening, okay, nature, regular work hardening nature. So this kind of nature, okay, if you see, we people call, okay, yield point phenomenon. That material is exhibiting yield point phenomenon. Okay, I hope, I think many of you aware of this thing, I guess. Okay, let's, because we need to have a discussion about, okay, why do you see, okay, such kind of nature, okay, in a yield drop. Okay, yield for yield, there's a drop in stress, yield stress, and followed by some slight serrations, almost like a constant stress, but there is a significant amount of strain, okay, significant amount of strain, okay, at a constant stress. Then following a regular, okay, this regular thing basically related to work hardening, okay, that has been already explained. Okay, now we need to focus on this, okay, part. Okay, so the, where the stress is start dropping, okay, that stress is called upper yield point, and where the stress is fluctuating, okay, that stress is called lower yield point, upper yield point and lower yield point. Okay, the whole thing is called yield point phenomenon. So can anybody say what is causing this upper yield strength and lower yield strength and serrations in the behavior? Let's have a discussion, okay, because I want to see how much you already understood about this yield
Sir,
point.
when the interstitial atoms interacts with the core of the edge dislocations,
Mhm.
so there is a pinning and unpinning of these interstitial atoms.
Okay.
So it gets trapped in the quartal atmosphere of the dislocation core of an edge dislocation.
Mm-hmm. Okay. Now explain why do you get upper and lower yield, and why it is fluctuating. Okay, that's what I wanted.
Sir, it is fluctuating because when an atom goes into the dislocation core, it makes it difficult to move the dislocation. So
Then
the
that
stress is
stress.
increased.
Yeah, but I'm just start from here. Okay, why the stress is dropping first? Any idea? Because why it initially
No,
why it
sir.
is high, then after that why it is dropping, then it's like after that what you're seeing.
No, sir.
Okay.
Sir, I can take a guess.
Yes.
I did actually read about this, but I don't completely recall it. So I'll just take a guess. So it's I think where the dislocations get piled up, and then in there is something called a quartal atmosphere where there are where the impurity atoms go, and then when it goes up to the upper yield point, the co- the concentration of the impurity atoms is a lot, and then it bursts through, and then the dislocation density kind of reduces because it bursts through, and then it becomes easier, and then the yield stress goes. Uh, Something like that, sir. I don't recall it completely.
Okay. Fine. Yeah, I think see both of you given us some picture. Okay, about this thing. Okay, it revolves around that. Okay, you used some of the terminologies. Okay, atmosphere, you said, and interaction with the, okay, dislocations, interaction with solute atoms. Okay, those kind of terminologies both of you used. Okay, so you have to remember that, okay, this kind of yield point phenomenon not only observed in steels, okay, can also be observed, okay, other materials. Cadmium, people have shown in cadmium, if it contains some interstitial okay, atoms, can give you this kind of problem thing. And okay, the drop in yield stress, okay, for example, like this drop as also has been observed, okay, though they may not see such a okay, significant constant stress thing. Okay, so what people have seen, this drop in yield stress in some, okay, some ceramic compounds also, lithium fluoride kind of compounds also, people have reported, okay, the yield stress drop in the material. So because of interest, okay, steel is a very much important component, a very much important material as far as fabrication is concerned. So usually we do fabrication, okay, in the, okay, plastic deformation region. Okay, actually if you want to make a component out of a steel, many times, okay, the fabrication involves some amount of plastic deformation. Okay, so this kind of, okay, if you see this kind of stress strain behavior, okay, it is not good for a fabrication. Okay, so if the material exhibits this kind of, okay, yield point phenomenon, okay, that means actually that component will have some problems. Okay, a lot of severe problems is going to have severe problems. So one has to overcome this problem. Okay, so this can be first. Okay, that's one thing. Okay, this is not advisable to have it. Okay, though the stress requirement is going to come down, however, okay, this can lead to some serious issues. We'll discuss what is the serious issue we are going to see. Okay, so let's discuss. Okay, upper yield point and okay, drop in yield. Okay, drop in yield stress and constant, almost like a constant stress. What we are seeing. Okay, why do you see? Okay, all these three aspects. So initially, when you deform material elastically, okay, when you deform material elastically, okay, at a certain temperature and okay, strain rate, you are deforming material, assume that at a certain temperature and strain rate. Okay. Most of the cases, okay, when you talk about steels, typically around room temperature to some 100 degrees Celsius, if you deform, okay, we do see this kind of nature. Okay. So at that, okay, even at that temperature, okay, solute atoms, okay, interact with the dislocations. Okay, when you talk about solute atoms, you are talking about here interstitial solute atoms. Okay, why don't you talk about substitutional solute atoms? Substitutional atoms require, okay, because this solute atom interaction means actually there is some diffusion activity. Unless there is some diffusion activity, those do not, we do not see much interaction between the solutes and the dislocations. So the interaction between solutes, okay, and dislocations are, okay, basically going to depend on, okay, on actually diffusional activity of solutes and, okay, the velocity of dislocations, at what speed the dislocations are moving. Okay, the velocity of dislocations, okay, is going to depend on strain rate of material. Am I right? Okay, the rate of, at what rate you are deforming material, according to the velocity of dislocation also going to change. Okay, and the diffusion activity is going to depend on, okay, how much time you're giving, okay, for atoms to jump from one position to other position. That means we are talking about strain rate and temperature, both are going to play, okay, role on solute atoms interaction with dislocations. Is it clear? The first point you have to remember that both temperature and strain rate are going to dictate, okay, the interaction between the solutes and the dislocations. Okay, so I said, okay, I said this kind of thing can be seen only at a certain temperature range and strain rate. Okay, temperature and strain rate, there's a domain. Okay, within the domain only we do see, because we are talking about, okay, the interaction of solutes with dislocations, which basically function of both temperature and strain rate. Okay, so when you deform a material, okay, assume that first grain, okay, one of the, in the polycrystal, this can be seen not only single, okay, polycrystal can also be seen in single crystals. Okay, in a single crystal iron, which is having small amount of carbon, can have this kind of behavior. Okay, polycrystal materials also will exhibit this kind of behavior. Okay, just assume that, okay, the material started to deform. We are deforming material at a rate where this phenomenon has been observed. Assume that that phenomenon has been observed. When you deform a material, okay, at that rate, at a given temperature, okay, what happens? Okay, dislocations are going to interact with the solutes, because we are having a favorable okay, combination of strain rate and temperature, which basically facilitate, okay, which facilitates interaction between the solutes and dislocations. Okay, during elastic deformation itself, okay, we do see certain amount of, okay, activity is going to take place, these interactions. So when the solutes are getting, all assume that I have a certain number of n number of dislocation density. I have a rho, some dislocation density. So that number of dislocation density, okay, has a some field, stress field. It has a stress field. So at the stress field means we are talking about dislocation core has a some field. So what happened? These solutes can interact with those, okay, stress fields, can form an atmosphere. Okay, that means basically locking. So dislocations can be locked by solute atoms. Okay, during elastic deformation, even actually at room temperature, you have some interaction. Okay, when you deform them, okay, at that rate, we do see some interaction between, okay, dislocations and solute atom. So there is an interaction. Okay, we are talking interaction. So that interaction gives us an atmosphere called, okay, locking atmosphere, is also Cottrell atmosphere. People call Cottrell atmosphere because he was the first one who pointed out that when there is a solute atoms, interstitial solute atoms, okay, those can actually can lock the dislocations, can form an atmosphere around because of stress field present in the dislocations. So the material which is already having a dislocation, some of the dislocations have been pinned down. Okay, when you apply a certain rate of deformation, that means dislocation trying to move. try to move. Okay, so that when the dislocation is moving, okay, at certain amount of stress, once it reaches, when you apply certain amount of stress, the dislocation can get unpinned, can get unpinned. Okay, so the unpinning, that unlocking, this is unlocking, we are talking about locked in initially. So after certain amount of stress is reached, you are unlocking the dislocations. Once you unlock the dislocation from solute atoms, okay, dislocations move freely. Okay, that means what you are talking about, the stress required for unlocking is higher than stress required for moving the dislocations. So that is one of the reasons for drop in the stress. Okay, is it clear? Locking and unlocking, okay, are two activities, okay, which contribute to, okay, upper yield and lower yield in the material. Okay, and after that, once you unlock them, okay, once you unlock, okay, because you have solute atoms separately and dislocations are having mobile dislocation, it can mobile, can move very freely. Okay, so that can lead to some instability in the deformation. We are going to see some unstable plastic deformation. What does mean unstable plastic deformation? Actually, we are now actually solutes having its own interaction. Okay, solutes are move, okay, having been already have within a grain, okay, which may be having some velocity because of your diffusion taking place because of temperature and strain rate. But dislocation is also moving it freely, okay, very fast. So that can lead to a kind of unstable plastic deformation. This is called yield point elongation. So this elongation is called yield point elongation. Okay. After certain amount of dislocation density has been developed, once more and more dislocation gets built up, because we know that during deformation, more and more dislocation can get generated. Okay, can get multiplied. Once multiplication happens, lot of multiplication happens, then we are going to see regular, okay, plastic deformation behavior of a material. Okay, so during this, okay, during this yield point elongation, okay, where we are talking about instability and deformation, it's one of the plastic deformation instability, okay, instable domain. So this can lead to formation of some bands. Those bands are called lotus band. Okay, okay, so if I take, okay, a stress strain curve, just only this region 1 2 3, okay, these three regions, if I take a tensile specimen, okay, what happens once we have, now already we know, okay, there is a drop in yield stress, okay, that means dislocations have been freed. So when the stress drops to this level 0.1, okay, it is the tensile specimen going to see formation of a band structure. Okay, this band is called lotus band. Okay, lotus band. Okay, it will form around 45 degrees. Okay, between 45 to 70 degrees angle, it is going to form. Okay, where it is going to form? Wherever the stress concentration region present in a specimen. In a tensile specimens, the first stress concentration region is always like a fillet region. Okay, the fillet region will be having a stress concentrated region. So that's why we do see the band formation. Okay, do not get confused, these bands are nothing to do with the slip lines and slip bands. These are actually different from slip lines and slip lanes. These are called, okay, simply called lotus band. These bands are going to form, okay, at a stress concentration region initially, and these will propagate, these bands will propagate, okay, from one position to other position of the, okay, entire gauge length of the specimen. Okay, going to see propagation of this, okay, band. Okay, so this band propagation, okay, can happen, can be multiple bands can generate. Okay, depending on stress constant regions, okay, depending on stress constant regions, we may see multiple bands can generate or single band, depending. If the stress constant is only maximum at one position, we may see only one band. Okay, if the stress constant happening here and there, then from both sides bands are going to form. Okay, so this band propagation, okay, is going to happen at a constant stress, constant stress. But because of band propagation, the material is going to experience strain in the material. Okay, so that basically formation of multiple bands can give you, okay, serrations in the material. Okay, the serrations whatever you're seeing, okay, is basically resultant of loader bands, how many number of bands are forming. Okay, that can, okay, if it is only one band, we do see very nice line. Okay, but if there are multiple bands are coming from other side, both sides, okay, then we do see these serrations are going to form in the material. Okay, so the stress strain behavior is going to see this, okay, though it's constant because it's entirely related to a formation of a this smooth band, whatever you're seeing, this band formation and its propagation can lead to this yield point elongation in the material. Okay, is it clear? Is it clear or not?
Yes, sir.
Yes, sir.
Okay, so it's not, story is not end here. Okay, though this one slide we can say everything about how it is forming. Okay, so if you look at when was it reported? Okay, if you see here, okay, sorry, before that, okay, when this kind of bands form, okay, that non-uniform elongation, whatever thing, okay, it's non-uniform. People consider it's a non-uniform kind of elongation. Basically, it's instability in the material that can lead to formation of a this kind of stretcher strains. Okay, the bands, whatever thing, the bands are going to propagate. Okay, one can see with the macroscopically. If we do a well-polished sample, we can get a bands. So, but those bands can actually, with further deformation, okay, with the deformation, okay, can undergo, gives rise this kind of stretcher strain marks. Okay, if you take a sheet, if you stamp it, okay, low carbon steel, if you stamp it, okay, that can give us this kind of okay stretcher strain marks. Okay, so these formation of presence of these stretcher strain marks, okay, are basically resultant of yield point, okay, phenomenon. Okay, whenever there is a yield point elongation, okay, can gives rise, okay, this kind of stretcher strains. Okay. So this formation of stretcher strains is considered as a problematic thing, okay, for a component which has been fabricated, okay, without overcoming this problem. If we directly fabricate it, we do see this kind of bands. What is the problem here? Tell me. This stretcher, if the stretcher strains are there on a sheet of a fabricated sheet material component, what is the problem?
Appearance, sir.
Okay, so basically we are basically generates locally some roughness in the material. Only appearance, anything else? Is there any problem? Yeah, you're right, because appearance is the major problem, because there's a surface roughness. So smooth, because we usually want to have components with a smooth surface finish. Okay, but if we have this kind of problem, that is gives us a rough surface. So rough surface always a problem for components, especially when you talk about fatigue, deformation, and corrosion. Okay, fatigue and corrosion, these are surface phenomena. Okay, so fatigue usually happens at the surface. Start the crack initiation under cyclic loading conditions happens on a surface of material. If there is a surface roughness, that can give you easy crack initiation. Okay, then that crack can propagate with a less number of cycles. The component can fail. Similarly, corrosion can be concentrated in the rough regions. Okay, so you do see non-uniform corrosion. The smooth surface have less corrosion, whereas rough surface will have a high corrosion. So these are the problems. Okay, we are going to see if there is a yield point phenomenon, the material is exhibiting yield point phenomenon, that can lead to stretch strain lines in the material. So this observation, whatever you're talking about, okay, it started way back in the 1842. Okay, these are the first people who reported formation of a this stress drop and formation of some serrations and formation of these lines has been reported by and this has been look at here, loaders was the one who has seen these materials. When he tested, he has seen the when well polished sample, he has seen formation of that loader bands. A band is forming and propagating. That has been reported by loaders in the year 1860. In order to explain what I said, unlocking, locking, and loader bands formation, everything, people have explained after 100 years of its first report around 1949, Cottle and Bilby, they explained, first explanation was given, why there is a upper yield point, why there is a upper yield point. Okay, the drop they could not explain properly. Okay, they said there is a, it falls. Okay, then after that, why it actually undergoes such a transformation, such a deformation, they could not explain. But this is the kind of thing what they used, using Cartel atmosphere, presence of solute atoms can interact with the dislocations and can lock the dislocation movement, and after that unlocking can take place. That's what the kind of thing they explained from the by Cartel and Bilby. But that kind of stress drop has been observed not only in solutes containing alloys, not only alloys, it also has been observed, okay, in lithium fluoride, other crystals which do not have any solute atoms. So there actually this Johnston and Gilman, okay, these were the people who have clearly explained why do you see a drop in the, okay, stress, a drop in a stress even in materials do not contain solute atoms. Okay, so these two theories, okay, are being used to explain, okay, formation, okay, the formation of yield point phenomenon in a material. So according to Johnston Gilman, okay, is very interesting phenomenon, okay, has been explained by Johnston Gilman. So okay, using a simple concept of, okay, dislocation movement, okay, dislocation velocity. Okay, so I'll come to that little bit. So whatever I said, loader bands in steel form at angles with a tensile axis 45 degrees to 70 degrees. Okay, and sometimes we do say single loader bands. Okay, multiple bands can also form. Complex bands also form. When complex bands forms, that can lead to stretch strains in a material. Okay, the plastic deformation observed whatever. Okay, it is not a simple pure. Though we consider it 45 degrees, since it's happening at 45 degrees, it's not pure shear deformation. Okay, it's a combination of shear deformation and deformation perpendicular to load of current. Okay, there are actually two deformations. Okay, the mode of deformation, okay, shear deformation along with a another, okay, perpendicular to the load of band front can both contribute to plastic deformation, okay, in the material when the loader band propagates from one location to other location. Okay, so people have difficulty to explain the temperature dependence of yields phenomenon and level of the, okay, lower yield strength, how much low it can go down. Okay, so we have observed there's a drop, how much low it can drop. Okay, there was a lot of difficulties people are facing. Even, okay, I'll tell you, okay, this research is not dead. Okay, still going on, okay, to explain, okay, some of the yield point which are not being explained using Cartel Bilby or Johnson Gilman models. People are still trying to, okay, see using new, okay, what are advanced characterization tools. People are trying to observe again and explain the yield point phenomenon in materials. Okay, so one of the so far common explanation, okay, is using Carter Bilby theory and Johnston Gilman models. Okay, according to Johnston Gilman, okay, theory, okay, what it says, the necessary criteria, okay, criteria are an increasing number of moving dislocations. One has to see a number of dislocations. Okay, the moving dislocation, the mobile dislocation density has to increase. That's one necessity criteria, and there should be a direct relation between the stress and the velocity of a dislocations. Okay, in certain, okay, materials, alloys, presence of interstitial solutions also is a necessary criteria in some materials. Okay, not all materials. So the actual basic necessary criteria are these two. Okay, so according to Johnston, okay, Gilman, okay, what are we talking about? This model basically tells that the yield point phenomena can be observed when there is an increased number of moving dislocations, and there exists a relation between stress and the velocity of a dislocations. So what this model said, okay, velocity, okay, dislocation velocity is a function of stress and temperature, as a, okay, function of stress and temperature. Okay, so velocity is basically proportional to sigma m. Okay, so sigma m is some exponent, and temperature is considered here. Okay, so according to this model, what they used, okay, the simple Vorovan equation, simple Vorovan equation, which basically describes, okay, I think in one of my previous lectures I said strain is proportional to rho b l. Okay, here actually strain rate is basically b. Here actually n consider as a rho, because I just simply taken information from this paper. Okay, you can consider n is equal to rho here. Okay, rho is the dislocation density, b is the Burgers vector, v is the, okay, velocity, okay, average dislocation velocity. So the local strain rate, when you are applying deformation, okay, certain rate, but locally the rate of deformation is going to depend on, okay, dislocation velocity and dislocation density. Okay, if you take a represented volume in a material, okay, I'm deforming material at a external strain rate, some epsilon dot s. Okay, I'm deforming at a particular rate. Okay, but locally, okay, the local strain rate in any given volume of a material is basically can be taken from a Vorovan equation. Strain rate is basically function of dislocation density and dislocation velocity. Okay, so this basically, if you take both edge and screw dislocations, we do get, okay, this kind of equation. If you consider, okay, usually edge dislocation loops move about 50 times as fast as screw components. That's why most of the explanation will be used, okay, will be using edge dislocations, not much screw dislocation, because edge dislocation can move faster than screw dislocations. So if I consider this about 50 factor, okay, one can simplify, okay, the dislocation density. So, okay, the dislocation density can be taken as a simply dislocation density of a, okay, material. Okay, so one can take, okay, this kind of, okay, equation to describe dislocation density. So according to this theory, this model, what it says, the dislocation density is, okay, proportional to 10 to the power of 9 to the power of strain. Okay, what does it mean? With increasing strain, the dislocation density is going to increase. However, if you see here, according to this equation, even if you increase 1% of strain, even if you increase 0.1% strain, okay, the amount of dislocation density initially is very high. Okay, so because of rapid increase in dislocation velocity, okay, initially, okay, that can, okay, lead to instability in the deformation. Though I'm applying a particular strain rate, but locally I do see very high strain rate in the material. Okay, so that can lead to instability in the deformation. So as a result, we can see, okay, drop in the, okay, yield stress of the stress of the material. Okay, so that is the kind of explanation given by Johnston and Gilman, just to, okay, why there is a drop in the yield stress in the material. Okay, is it clear? There's a lot of things, okay, I think in from this model, I just taken some glimpses of the model, what it says. Okay, any doubts here? I think just came through what I mentioned in this slide.
So this Johnston Gilman is also applicable to solute LOI solution material, which
Yes,
is
yes,
having a solute.
yes,
So it's a
yes,
universal.
it's applicable. Okay, it's universal. It's okay.
Okay.
Only for actually to explain, okay, why there is a from okay, upper yield point to the drop. That has
Yeah.
that curve. Okay, that drop has been explained using this model. Okay.
Elongation also, no?
Yes. No. Yeah.
Till
Just drop to drop up to lower yield point. After that, okay, that's a different story. Okay, the survey, whatever you are seeing, uniform. Okay, some elongation you are seeing at a constant, that's a different story. That what
but
initial
the
drop, okay, whatever has been.
Luder's band is explaining till yield point elongation.
Yeah, that's loader band concept. Okay.
Yeah, that is giving
What you are
information
seeing,
till
okay.
yield point elongation, but the Johnston
Yeah,
Gilman
but
is
that will
giving
not
till.
say about upper yield. I'll tell you. No, that will
Okay.
tell you. Okay.
Okay.
Cotton Bilby theory, it just says, okay, upper yield, okay, then sudden drop. Okay, but they didn't say how this drop is going to take place. Okay.
Okay.
That they simply said there will be a drop. Okay, that's what they talked about. Okay, but it will not say how the drop is going to take place. Why the, okay, how the drop is going to take place, that has been given by Cottle and Bilby. Okay.
Okay.
Whereas Johnston Gilman, they have explained how the drop. Okay, why do you see such a, okay, exponential drop or whatever that equation you are talking about? Okay, why that changing? Okay, and whatever is seeing the constant strain or the constant stress deformation, that has been given by loaders.
Okay.
Okay, you
Okay.
have to remember that there are three things, okay, here. One is a Cottle and Bilby theory, and Johnston Gilman theory. It basically talks about upper yield to lower yield point. Okay,
Okay.
these two theories basically talks about, okay.
Okay.
Any
Sure.
doubt? Yeah, you're saying something.
No, sir. Understood.
So what you are talking about, okay, the loader concept is basically related to the constant stress deformation. The deformation at
Yeah.
constant stress, whatever it is seeing, that has been explained
Okay.
by loader band.
Okay. Sure.
Okay.
Thank you, sir.
Sir, again, how is
Any
the
more
drop
doubts?
getting explained in this equation number 11? The drop, where is the stress relationship with the strain rate?
Okay. So the value for M, okay, typically, okay, it is like this. Okay, if we talk about, okay, if we, okay, with increasing stress, okay, we are deforming at a particular rate. Okay, at a particular rate. Okay, the rate is fixed. External rate is fixed. Okay, internal rate, okay, the internal strain rate, is a function of stress. Is a function of stress. Am I right? Okay. The velocity of dislocation is a function of, okay, velocity of a dislocation is
Yes,
function
sir.
of a stress. If I put this, okay, in this equation, okay, in this equation, okay, if I take in this equation, the finalized, okay, the final equation, if I take, okay, if I put here, okay, what happened? Your strain rate is locally, okay, I'm talking about, okay, inside of the represented volume, okay, your strain rate is increasing. Though I'm deforming material at a particular strain rate, my internal strain rate, okay, at a given represented volume, okay, is locally it's increasing. Okay, its strain rate is increasing locally until maximum stress upper yield point, up to the upper yield point. After that, what happens? Okay, it has to maintain. Okay, the internal strain rate has to be maintained with the external strain rate. The balance has to happen. Okay, that means what should happen? Your velocity of dislocation should come down. Am I right? In order to decrease strain rate further.
Okay,
So
so
initial, okay,
velocity is the
I'll talk
internal
about this.
strain rate, you're saying?
Yeah. So now, okay, if I take, okay, yeah, velocity internal strain, okay, velocity of a dislocation is a function of a stress. With increasing stress, okay, what happens? Dislocation velocity is increasing. Dislocation velocity is increasing. Am I right? Once you increase the strain rate, okay, that means the dislocation velocity is directly now actually going to influence my internal strain rate of the material. That means though I'm applying a particular strain rate, initially in small amount of deformation can lead to an increased, okay, strain rate locally. Okay, so there is going to be an instability region. That means actually your strain rate, external strain rate is fixed, okay, at constant strain rate, but internal strain rate has been gone up. Okay, so but what happened? In order to maintain a balance, okay, the material has to deform at the same rate of external rate. In that case, what should happen? Your, okay, strain rate should come down to your equal strain rate what you are applying externally. So that drop can happen only, okay, only by decreasing the velocity of a dislocation. When can happen? Once you, okay, so that is the kind of thing. This how this drop is taking place was explained by that equation. Okay, so this equation basically tells, okay, your velocity of dislocation is proportional to stress. Once it reaches, okay, set upper yield stress, okay, that internal strain rate is higher. Okay. However, what happens? In order to maintain a balance between the internal and external strain rate, okay, this has to come down. But actually, your, okay, dislocation density already increased a lot. Okay, so the increased dislocation velocity can bring down the velocity of a dislocation. Okay, if you talk about no solutes are there are no solutes are there. Okay, so that's the kind of, okay. So the dislocation velocity can be come down. Okay, only, okay, in order to maintain a stability in the deformation, to deform the material at the same rate, okay, of what you are applying. If it does not deform, then it's going to get, okay, failed. Okay, the material is going to fail miserably. Okay, if the rate of internal deformation is more than external rate of deformation, so we are going to see a lot of, okay, straining in the material can fail. Okay, but it will not fail. It is not fail. Since the material is not failing, what does it mean? Actually, your dislocation density is locally, okay, velocity dislocation density is already increased, so that can lead to a reduced velocity. That means, okay, we are going to see a lot of multiplication. All those things can bring down the velocity of a dislocation. So that decrease in velocity, okay, is going to give you that drop in a stress in the material. Okay.
So basically, I is the internal strain rate, and that is going to saturate in some time with the increase of stress and thereby the increase in velocity. And when that happens, to maintain a balance between the internal and external strain rate, the velocity is going to come down, and with
Yes.
that, the stress is going to come down, and you see the drop in that curve.
Yes. Yeah. That's what. Once velocity coming down, your stress also coming down. Okay.
Yes, yes, okay.
Okay, this model does not consider any solute atoms. Okay, it can happen. Okay, when there is a, okay, balance act happens between the internal strain rate and external strain rate, that can lead to a drop in a stress. Okay, Is it clear? So if we talk about Cartel theory, okay, so we are talking about, okay, carbon atoms, which are carbon and nitrogen atoms, which are actually interstitial atoms, which can actually, okay, log the dislocations. So how many solute atoms are required? Okay, what is the, okay, how much, what is the fraction of carbon atom I need to pin, okay, certain n number of dislocation density? Okay, if you, okay, you are getting my point. How many how much, what is the carbon content? Why do you say only low carbon? Why do you want to see, okay, high carbon thing? And within low carbon, how much carbon content is responsible, okay, for such a yield drop in the material? Okay, how do you estimate how much carbon atoms required, solute atoms are required to pin the dislocations? Any idea? Because see, we are talking about, okay, so material, okay, steel, okay, we are talking about a low carbon steel. It has some carbon content. Okay, how many carbon atoms are going to participate in pinning the dislocations? That going to depend on dislocation density. Am I right? Higher the dislocation density, one can expect higher the carbon atoms requirement for locking the dislocations. Can you say it like that? Because if I dislocation density, I need to have more and more solute atoms to, okay, have a complete locking of the dislocations. So if I take two materials, one actually fully annealed material, okay, other one heavily cold work material. Okay, same material, if it's a copper or whatever, take steel, so take steel, mild steel. Okay, if I take a fully annealed material and fully cold work material, okay, what does mean? Actually, annealed material means dislocation density is about how much dislocation density for annealed materials? Any idea? Typical dislocation density?
Sir, 10 raised to 6.
Yeah, it depends on units. Okay, you have to be very, okay, unless you tell the units, okay, you do not know. Okay. Yeah, typical 10^6 to 10^8 per meter square. Typically, we'll see. Okay, in that, okay, heavily deformed materials. That means when you deform material, we do see dislocation density can go 10^12 to 10^14 per meter square. Okay, if I, okay, estimate how much carbon atoms required for these two materials, you'll get surprised. Okay, see, this is a kind of, okay, taken, okay, information from this textbook. Okay, it's very good textbook where you can get a lot of information about yield point phenomenon. So if you see the number of atoms required, okay, number of carbon atoms required, okay, to pin the dislocations present in a, okay, in a, okay, annealed material, okay, 10^8 per centimeter square. Again, in terms of units, we have 10^8. Okay, so if you convert into meter square, you get according number. But 10 for this particular density of dislocations, we need to have just, okay, 4 in 10^-8, okay, the atomic fraction, the carbon fraction with respect to iron. In heavily cold work material, okay, if we take Nc by Nfe, it's about 4 into 10^-4. That means we need to have only just 0.04% of carbon, okay, to pin, okay, heavily deformed material which is having a dislocation density about 10^12 per centimeter square. Okay, so we need to have just only 0.04%. Okay? That much is good enough to pin the dislocations. Typically, we always do with start with a annealed material. Okay, because if we talk about forming a material, we always take a annealed material, which is easy to deform, okay, which is easy to form the thing. So if we take a annealed material, you don't need actually such a very, okay, amount of carbon. Very small amount of carbon is sufficient to pin all the dislocations, whatever initially available, okay, dislocations. Okay, this is a kind of calculation, basically simple calculation by using number of atoms required, okay, which are present in, okay, number, okay, in iron cube. By taking a BCC unit, we'll get, okay, this simple calculation. Just go through this text, it will give you a simple calculation how many number of carbon atoms are required, okay, with respect to, okay, iron atoms. Okay, just we need to have 0.04%. Okay, very little carbon is sufficient for, okay, forming a quartal atmosphere in a material. Okay, is it clear? Any doubts here? Are there any doubts?
Sir, so if there is no impurity, then that yield point phenomenon won't be seen.
in steels, okay, people did not see, okay, in VCC iron, okay, they did not, okay, this presence is very much important, okay, but I'll tell you, okay, it is impossible to, okay, almost like impossible to get a pure iron
Yeah.
by regular any production, okay. We always, okay, that's why actually we always will have a this much of percent, okay, carbon. Even if you go to very lowest carbon, extra low, ultra low carbon steels, okay, we'll have at least 40 ppm, okay, carbon. So that's good enough. So that means actually, so whatever steels you are producing, low carbon steels, okay, of such low carbon, even then also we do see this problem. Okay. If you get, okay, pure iron, okay, people, Cartel, they said we don't see such a, okay, different. People did not report also, okay, because it's very difficult to get a ductile pure iron, okay. People are producing by different routes, but it's not ductile enough, okay, because of processing artifacts is becoming brittle, okay.
Okay.
Is it clear? Okay, so we need to have a small amount of carbon such that can form Cartel atmosphere, that can lock the dislocations. Okay, so to unlock the dislocations, we need to have a high stress. Once it unlock, it basically requires low stress for the propagation, okay, for the plastic formation to take place. Okay, so there's a kind of concept given by Cartel and Bilby. Okay, and after that, because the Johnson gentleman is given very nice explanation why should there be a drop, because of, okay, instability in a strain rate of deformation within a material and external, so that can lead to a drop in the stress. Okay, so now I said this, it has a problem because this if you see a yield point phenomenon in a material, that can lead to formation of some, okay, irregular surface, okay, uneven rough surface is going to be get created. Okay, that is the kind of thing one has to be avoided. Okay, how do we avoid? What are the different methods available to avoid? Okay, I want to, because I have a low carbon steel, okay, for example, many of our, okay, sheets, refrigerator sheets, automotive, okay, car bodies, all of the most of these cars, regular, okay, conventional cars will use low carbon steels, but these low carbon steels which are in annealed condition will be used for farming, easy farming, but the problem actually, it's going to, what we are going to see is a yield point phenomenon. Okay, that can lead to a rough surface, so one has to avoid, okay, what kind of techniques one should use? Can anybody say what can gives, what can minimize, okay, or avoid, okay, one can, how to minimize or avoid the formation of stretcher strain marks
Sir,
during the,
can we do high temperature, because at high temperature the diffusion of carbon will be higher, and so this can be eliminated a little bit.
yeah, so but actually deformation always we want to do, okay, just when you go to higher and high temperature, the cost of production is going to be higher. Okay.
So sometimes we do. Hello. Sometimes we
Yes.
do hot stamping instead of cold stamping.
Yeah, that is for particular materials. Okay, for low carbon, we do not do hard stamping. Okay, low carbon, this actually plain carbon. I'm talking about, okay, plain carbon steels. Okay, what you are talking about hard stamping is slightly different. Okay, where Martin said, okay, coming to picture. Okay,
Rolling
regular.
stamp,
Okay, okay. Somebody says rolling. What rolling?
stamp rolling.
Yeah, so people call it, there are different terminologies, okay, skin pass rolling or temper rolling. That's one of the solutions. Okay, so what does it mean? Before going for a plastic deformation, which before going for fabrication, okay, the low, okay, annealed low carbon steel, okay, will be given small amount of deformation. Okay, how much amount you have to give? How much amount you have to give? Because we know that according to stress strain curve, okay, according to stress strain curve, there is a, okay, loader band strain, okay, what you are seeing, loader band non-uniform strain, what you are seeing, if you exceed that amount of strain, okay, we can see minimization of loader bands. Loader bands are going to get minimized. Okay, what is not minimized, it's not really minimized, okay, the roughness is going to be minimized. Okay, if we give about 1 to 2% of strain, about 1 to 2% of cold rolling, that's called skin pass, just only deform material, just pass, okay, the skin pass, our top layer, if you deform, give 1 to 2% of strain, that can, okay, minimize surface roughness on the material. It will not avoid, it will not avoid the stretch strain bands, but it minimizes the roughness of the material. Okay, so that's called skin pass rolling or temper rolling. Okay. Why do you say it's basically it minimizes means actually by giving the skin pass rolling, we are going to generate numerous stretch strain bands. We are going to see numerous fine stretch strains are going to form during further deformation. So if it is a very numerous and very tiny, your roughness is going to be smaller. Okay. So that's how actually the concept of temper rolling is coming to picture. Okay. So soon after annealing, before fabrication, one has to subject this material to a small amount of reduction. Typically, it comes around 1 to 2%. Okay, that's where actually we are seeing a uniform, constant stress strain. There is a strain at a constant strain. That much strain you have to give so that you can see. We can follow regular trajectory of a stress strain curve of a material. Because that strain depends on how much carbon you're talking about. How much so how much dislocation density is there. Accordingly, one has to decide how much strain is required for the skin pass. Typically for low carb stress, it lies anywhere between 1 to 2%. That's one of the solutions to control or minimize the stretch strain bands. The second method in steels, the major culprit what you're talking about, presence of these interstitial elements, which basically causing locking and unlocking that can lead to this kind of yield point phenomenon. If you can arrest those carbon atoms, we can arrest them without so that those will not directly interact with the dislocations. That means actually you need to arrest the carbon whatever is there in low carbon state, whatever is there. If you can arrest free mobile free atoms, free carbon atoms, that can also solve the problem. So in that direction, what people do, people add some carbide forming elements like a titanium, boron, aluminum. In case of a nitrogen, if I want a aluminum nitride, it forms. Carbon, titanium carbide or boron, some boron presence, boron carbide, boron nitride. So those can, avoid that can avoid the formation of this yield point phenomenon in the material. These are two well-established techniques. One, subjecting it to if we do not add any of those titanium or boron, those things what you should do, we should go for a temper rolling, a skin pass rolling. Small amount of reduction was to be given. The second one, you have to add this carbide forming and nitriding forming elements like titanium, boron, aluminum. So those can actually basically arrest this carbon by forming a compounds. Once the carbon reacts with this carbide forming or nitrogen forming carbide forming elements, then we don't have any free carbon which can interact with the dislocations. That can also avoid the formation of a yield point phenomenon. Is it clear about the yield point phenomenon?
So I didn't exactly understand point number one, so skin rolling. How giving a strain would avoid the roughness or sketch a strain band.
Okay, so when you go for because what you are talking about, this is my stress strain curve. If I do not do any skin pass rolling after annealing, if I do if I conduct a stress strain tensile test, I do get a like assume that this kind of stress strain behavior. This is about around, it lies anywhere up to 1 to 2%. This strain is 1 to 2%. So if I do skin pass rolling, if I deform material about 1 to 2%, just deform material, just only 2%, less than 2%. That means what happens? You are already deforming material up to this thing. Am I right? You already deform the material up to this.
Yes, sir. Understood.
Then if you go for a fabrication immediately, that can follow this regular trajectory.
So you're
Immediately
basically
how to do it.
bypassing the region that we don't want.
Yes, the by giving a skin pass rolling, we are basically deforming material up to this thing. When you deform material, when you give small amount of deformation, that basically can lead to that it will form stretch strains. But what was stretch strains are forming that can be a multiple slip band, multiple strains. Loader bands will be forming, multiple very tiny. We are nucleating multiple bands so that the stretch strain marks will be finer. The roughness is going to be much smooth. Okay. Yes.
So, sir, 1 to 2% strain that you want to give, at what
Mhm.
point on the curve do
Here,
you give
just
it
we're
to?
crossing this. We just crossed this line. Okay. We
Okay,
just
okay,
crossed this horizontal thing.
okay,
Once you cross it, that's it. Okay. That means already, okay, by giving a compression rolling, we are talking about rolling, which is a complex stress state. That can lead to formation of multiple loader bands. Okay. And those multiple bands, what are forming, okay, are like a very tiny bands. So that can lead to a reduced roughness of the surface.
So, but the bands forming thing
Okay.
was only in the horizontal section, right? So, if you are bypassing the horizontal section, then there should be no bands, right? Because
No, that means, yeah, it's already, that means whatever before pre-fabrication, okay, before fabrication, you'll be having roughness, but that roughness is much smoother,
okay,
relatively smoother than if I do directly forming.
okay.
Okay.
So the bands in the horizontal section, which could be there if you didn't do this, you didn't do this activity in the pre-strain that you do before the fabrication. Over there only you are forming these bands which are of a smaller size, right?
Yes, you are
Okay,
right. Yes. Because what I'm talking about here is tensile stress strain curve. That is a fixed, okay, mode of deformation. Fixed mode of deformation.
okay,
Okay. If I deform material, I get actually like bands. Okay. The coarser bands will be there. If I go for a cold rolling, okay, if I go for a rolling, which is a complex state of stress, that can lead to loader bands. Okay. Because prior deformation can give
yes,
you loader bands, but those are like multiple bands. Okay. Multiple directions going to happen. Because of multiple bands, matrices are tiny in shape. So that can lead to a relatively smoother or less rough stretches strains. Okay, once if you relatively stretch like a tiny thing, it's okay. Then you can go for a fabrication. Okay, then we are fabrication start directly here.
okay,
Is it clear about the temper rolling condition? What you are giving? Okay.
yes,
So one thing you have to remember, I'll stop it on this slide. Okay. One thing you have to remember that. Okay. So for example, it was temper roll. Okay. One of the things. Okay. For example, this steel was a temper roll. Okay. When after temper rolling, if I go for a tensile testing. Okay. I do get a very smooth curve. Okay. This okay, because already you overcome that one. Okay. Now it already has a certain amount 2% of strain. So if it deform material under tension, okay, I do get a nice stress strain, okay, curve because it's following the regular trajectory of the stress strain behavior. However, if I deform material, okay, at 100 degrees Celsius, okay, this was shown at 50 degrees Celsius, it considers room temperature. Okay, if I age the material 1 hour, okay, if I age the material at 100 degrees Celsius for 1 hour, okay, I do start seeing, okay, depending on temperature, with increasing temperature, okay, the aging temperature, I'm talking about aging temperature, 1 hour aging is done at different temperatures. With increasing aging, what happens? Reappearance of, okay, reappearance of this, okay, yield point phenomenon is going to be seen. Okay, so this is called, okay, this is called, okay, aging. We are talking with aging. Okay, aging means to keep the material at the temperature, okay, and hold it for a while. Okay, and if you deform at room temperature again, deform material at room temperature, then we do see reappearance of, okay, this, okay, yield point phenomenon. Okay, so this is called a concept of strain aging concept. Okay, it's not really strain aging, it's a thermal aging, okay, effect. This is a thermal aging effect. What you are seeing is a thermal aging. When you give some, okay, some thermal activation, what happens? Your this, okay, carbon atoms again, okay, can get, okay, come out, and again we do see formation of unlocking locking phenomena is going to take place. Okay, so that aging, what happened? Stress also going to increase. Okay? Your yield stress is going to increase, but follows, okay, okay, yielding after yield point phenomena, again it follows a regular stress strain behavior. Okay, so I'll stop it here. We'll discuss about strain aging phenomenon, which is basically an extension to yield point phenomenon. Okay, after that strain aging, we talk about dynamic strain aging and Potvin Lee Chartler effect. Okay, so I'll stop it here. Now it's around 12:25, I guess. Okay, if there are any doubts, okay, let me know.
Sir, if we
Yes.
use interstitial free steel, then
If
is it
you,
going to help?
what is
IF
that?
steel, in interstitial free steel.
Yes, there actually we add titanium, okay, to okay control this titanium. It forms titanium, titanium carbides. We are
Uh,
arresting the free, okay, free. There won't be any free carbon in that. That's why I call interstitial free carbon steel.
sir, then Luder band will
Should not form.
decrease or
Should not form. Actually, okay, loader band should not form in those IF steel materials.
okay. Sir.
Any more doubts? Yeah. So before I think okay stopping today's lecture, okay, now I think it's a high time for us, okay, because we'll be having only one more lecture before midsem week, okay. So next Wednesday we'll be having one lecture, then Friday is holiday, okay, then your midsem exam starts. So there is no midsem exam for this course. I guess all of you know, okay. So that's a kind of announcement, okay. So there's no midsem exam, but we'll be having one lecture before the midsem week, okay. So, but I said before the midsem, okay, we will discuss about the term papers. Okay, in order to okay release the term paper topics, okay, you can form a team of maximum 2 students. So you can okay form, you can discuss with another student. You can form a team of 2 students. I would like to have that list, okay, by Tuesday. Okay, I will share a Google Excel sheet, Google spreadsheet. There you can okay mention who is your partner, okay. So that actually on Wednesday I'll come up with the topics, okay. There, okay, randomly you get the topic, okay. I'll decide the topics, okay. The titles, I'll give the titles of the papers, okay, which will be selected by lottery. So you'll press a one number. So at that corresponding number you'll be having a topic, okay, title for the paper, okay. So that is the kind of I think procedure I'm following for term paper, okay. So now you can come up with a team of okay maximum 2 students, okay. That means okay if you don't find anybody, if you want to work alone, it's also you're allowed, okay, you're welcome to do that, okay. But my I think suggestion, preferable thing is a form a team, because that's very much important, okay. During student life you should have a kind of okay interaction with other students. That's my intention, to come up with a team of 2 students, okay. If you feel that no, actually I don't want to interact with you, I want to do alone, that's okay, that's absolutely fine, no issue, okay. So the term paper can be done up to maximum 2 students together as a team for a given okay, title of the paper. Okay, I'll discuss other okay instruction. I'll give other guidelines for the term paper. Okay, on next at the next class on Wednesday. Okay, so by Tuesday, I think today evening or tomorrow, I'll just share a spreadsheet. Okay, you can form okay a team with your okay fellow students of this course. Is it clear about the I think instructions related to term paper? More instructions will be given on Wednesday, okay, about how to okay what is the thing okay I do expect from a term paper, okay, because term paper is constitutes okay almost 30 okay 30 marks.
Okay, sir.
Okay, so I think with this I think I'll stop here. Next lecture we discuss about strainaging and dynamic strainaging aspects of the material during plastic deformation. Okay, so I'll stop recording. If anybody has doubt, they can stay back. Others can leave. Okay, feel free to yeah, you can leave. Stop recording. Okay.